Change to full square. Flash. Okay, we'll start. Okay, today is our 8th reading group meeting, and today's presenter is Zeeshan, and he's going to talk about 3D dynamic representation of the environment.
Right.
Yeah.
So hi everyone, good to see all of you guys here. Shall I start, or more people will be joining in? I think.
Oh, you can just start.
Yeah,
I think you can just
start sharing. Okay, cool. Okay, so guys, today's paper is about the idea of how can we represent a scene in front of us, like scene that will be seen by a robotic manipulator camera, or or even by a wheeled mobile robot. The idea is that the scene keeps on changing, or it will be dynamically getting updated. So how can we keep a track of that kind of scene, and how can we represent that kind of scene? So there is this paper from, the name of the paper is this thing only, Learning 3D Dynamic Scene Representations for Robot Manipulation. So this is from Shuran Song's lab. I checked some of her Google Scholar work also, which seemed kind of like similar work only. Similar work, I mean, in the sense that for certain robotic tasks, how can we carry out the visual representation of the world around us? So that is what her lab generally works upon. This seems like a really interesting task because I think shouting in our lab has worked upon something like this, like object permanence filters. I think shouting and Herschel. So his work that he submitted to Roman was something along that line. And this thing will also be helpful because it ties back, or like it kind of hints towards active perception, which was a very cool idea back in the days when there was not so much of learning-based methods. And when Rosana's birthday was here, so I do remember that Shankar Shastri in that presentation or the event that happened, he pointed towards the importance of active perception and why it is quite interesting. So I will definitely try to hint towards that as an offshoot in this presentation. So this is how it is going to be, guys, the introduction and motivation part. Then, first of all, pardon my typos because I did it in like almost 100 words per minute. So sorry about that. So what are the crucial factors in understanding a scene? Like how do human beings like us understand the scene around us? And how can we impart those kind of abilities to these learning-based systems? Now, this is the name of the model, DSR, Dynamics Scene Representation, or 3D DSR, what Dr. Song has proposed. Some related work. So here we will talk about active perception. So how exactly, the parts of DSR and how exactly it works. What are the benefits of it? For the particular task in this paper, how she generated training data in the real world, in the simulation world. What are the metrics for evaluation, and what are the takeaways from it? So yeah. So the basic introduction is that most of the approaches that we have in the real world for tracking things moving are mostly 2D, like optical flow, which is a 2D based approach because it works on singular images. So modeling the world in a 3D format is kind of tricky and not widely used. And some of the works that are present, so what they do, they model, for example, like if very visible. For example, if a person is sitting here and something is occluding his view, then something is being moved, so it will be only partially detected. So a partial part of the object will be detected while being moved. So in the cluttered environment, occlusions do affect how those things are being tracked, and it creates a kind of appearance. For the representation model, for the 3D visual representation model, it will create a kind of appearance that hey, something was completely hidden there and something reappeared, something like this. So for the representation model, it will appear like that. So the goal of the model is to learn a persistent representation that kind of keeps a history of how the things are evolving over time. And yeah, and the second thing is that I think I did not focus upon that part. Okay, so robot manipulation is quite interesting because what they are trying to do in this paper is that can we use robot as an interacting mechanism in a scene or an interacting agent in a scene? And using that interacting agent, for example, a robotic arm is placed like this and it is like pushing it like this. So this is how we are creating a dynamic scene. And can we keep track of this thing hidden behind something else? So hidden behind something else, can we keep a track of this thing? So they are trying to have a predictive modeling approach for this visual representation. And it is going to be a 3D approach, it is volumetric representation. It reconstructs the object, like if it is coming out from somewhere, out of occlusion. So some part of the object that is, okay, I'll talk more about how the reconstruction part is going to happen later on. And keep on predict the motion under robot interaction. So yeah, the three crucial factors that actually she has highlighted 4 crucial factors. One is about her particular network. So I just taken 3 of them because those are for human beings also. So one being permanence, that objects disappearing from view and then reappearing on the other side because of the motion. So that should remain persistent. That hey, we have been like tracking that particular object moving in the scene in this particular manner. So that thing should be something that is comprehensive, or it remains consistent over time. The object was moving like this, so it appears along this direction and not like in the any opposite direction or in any other direction. A model completeness. I do want to ask about the word a model. I checked about this. I am not very sure, but first let me explain this word. So a model completeness is that partial observation of the scene happens, or like partial observation of a particular object happens, and in the dynamic, this particular DSR tries to complete the occupancy grids which it may be occupying. So you may be seeing a partial cube or a partial cuboid, and or a partial mug or a partial water bottle, and it will be completing the grids which it assumes that it will be like occupying. So it will be completing the object in this way. And here's a question to you guys. I do remember that sometime back in our lab presentations during the last spring, someone mentioned this term A model. I don't remember who, and I don't remember under what context they mentioned it. Perhaps it was some PhD who mentioned under some of their work, because I remember Laura was sitting beside me and she asked like, what is the meaning of the term A model? So any recollection from that? It was somewhere in spring.
It was Shafaq's presentation. Yeah.
Shafaq. Okay, so I'll reach out to her, because what I could get was that it is like non-modular or something like that, but I could not like make complete sense of it. Okay, thank you. Spatial-temporal continuity, which is again that over space and time, like the motion was happening, it remains constant, or a continuity is maintained. And we will discuss more about the continuity part later on. So, okay, this is I have this part. Okay, so very simple. So this is actually the experimental setup. What they are having is a UR5 robot. They are having 4 to 5 different kinds of objects in the scene. So they are having a cuboid. They are having mugs of different sizes. They are having certain water bottles. They are having certain like a sofa kind of system or Lego block sets like this. So these are the kind of objects they are putting in the scene. Now, what they're trying to just like in this particular image, what they're trying to show is that what a truncated sign distance function representation of the world looks like. So this thing is being moved here. This thing is being moved out here. This is being like passed around it completely, and we can see that. And from here onwards, this thing is being moved. This particular mug that is placed behind. So this one is being moved on the opposite side. Is he there? Okay. Just for the, should I do it for the Zoom or not? Like in the t equal to 1 and t equal to 2, the cylindrical object is being moved towards the right hand side, and from t equal to 3 and t equal to 4, the blue object that is on the rear side is being moved towards the left. So we can see that in these in the other approach, TSDF approach, occlusion is happening and objects are being partially shown here. That is one thing. And not very clear cut motion is also shown. Not very good, or here it is completely occluded. So we are seeing an object motion happening, but it is completely absent here. And this motion is actually like annotated by the people in the lab. Like it is not something that they are getting out of the representation TSDF. There's something they have annotated it here. But here we can see the red dots in the figure number C, figure 1 part C, the red dots are showing the motion direction. And even when the object is completely occluded, we have the representation of the object in the BSR representation, and we can see that the direction in which it is moving here. So the arrows are there. So this is just an example of how the dynamic scene representation is supposed to look like and how our model is behaving, like compared to another approach. We are going to dive deeper into this, but this is just a higher level overview of how the scene representation looks like.
Can you explain the DST?
It is a truncated sign distance function approach. So they are having a representation of this one from an overhead, not exactly overhead camera, but a side view elevated camera, and you can see that the objects are occluded from the view of the camera. So those are not created or not formed. So objects that are completely hidden here from the view of the camera. We can track the motion over time. However, it is not giving us that hey, the object is moving in this direction. Like any kind of understanding of how the object is moving, that is not being given by TSDF also. So both the things, like hidden objects are hidden, and the object that is moving in the next scene, it is shown to have moved over time, but the motion is not being captured, like how it is being moved. Unlike this one, like the red arrows here, these red blobs, actually they're like aggregation of arrows over each other. So they are showing the motion happening here.
Can you come to this later?
Yeah, definitely. Actually, TSTF is an approach they have not explained in the paper. So I may not be able to dive too much into it, but it must have been referenced there somewhere. Okay. So some related works which are in this direction. So there is this thing. I'm sorry, this slide is not very polished. So one is passive perception, which is a traditional task of extracting out an RGB image from a particular scene. Or if we are working on a depth data, then extracting out the depth image from the particular scene. So the depth image can be the form of clouds, or if we are representing it in the form of polygons for more graphical purposes. So it can be about those things. So this is like a passive perception task, just like extracting out the image or like taking in the image within the field of view. It can only work on static data. It cannot work on dynamic data scenes, and it has no understanding of dynamic scene. Active perception, on the other hand, is that camera viewpoint gets updated. So, and a very good example I remember, Pratik Chaudhary gave me was something like this, that we don't have a shelf kind of object here. Okay, so imagine that you have a scene in which certain objects are occluded because of, let's say that we are like arranging objects in a shelf. So in a shelf, like certain objects are occluded. So how can you as an observer move and come across so that you can see the occluded object? So that is, for example, we have eyes through which we get the input of the world. So the idea is that how can we update the camera viewpoint so that we are able to get a better view of the world. The occluded objects that are present there, we can get a better view of the world. So how can we, what control motion we should give to the robotic manipulator or give to the user so that we can get a better view of the world around us, or we can see the occluded objects, so like whatever object you want to manipulate at that time. So that is the idea of active perception, where the camera viewpoints are updated for exploration of the world or exploration of the world or map building kind of things. So those kind of things mostly used in RL task. And there was, so there is this work of Cheng and Katrina. I did not look into it, but it looks something like this. And Pratik put it very nicely, was, so let's imagine that you want to come across, you want to move yourself, or you want to move the robotic manipulator in such a way so that you get a good view of the world. How can you assure, or how can you guarantee that the motion you are doing of the manipulator is the right motion? Like, how can you say what you're doing is the best thing you are doing? So he said that this is a hot or a pressing problem in the world of active perception, which is still perhaps not completely solved. how can you say what you do is the best thing you do? So that is the question. He said is, I have not looked into this word, but yeah, I did put it here because it looks something like that. So, and I'm really sorry, these slides are not very polished here. So I'll just go through them mostly, like through the conversation part. And okay. And the third one, which they are trying to use in this particular work, is interactive perception. So here the perception is helped by carrying out interaction with a user, with an agent in the world. And we are having active perception also does not have active perception also does not have any dynamic scene representation, because there is no signal or no way of knowing that emotion is happening. Like there is no element in the map through which we can know that motion is happening, because active perception is just like passive perception only. Just that here the camera mounting position can be moved because it is like now given some kind of control. It can be a manipulator, it can be a wheeled mobile robot, it can be a human being. So now it can be moved, but it's just like passive perception because there is no signal to track that motion is happening. So it also cannot takes care of the dynamic world. But interactive perception is something which can take care of the dynamic scene building, or because it is having a signal of how it can keep track of the interaction that is happening and how the world is getting evolved. Because of that. Any question before we move forward into the main model for today? Okay, just a quick glance at time. Okay, yeah. So the DSR net, or the dynamic scene representation. So what she has done, okay. Okay, so here are three things. Ignore this part, guys. I mean, ignore this part. So what they have done is that they have taken scene, they are creating a representation, and then they are putting it inside an encoder. The encoder is giving, that is the action encoder, sorry. So they're taking an observation and then they're putting it inside a scene encoder. So at any given time t, we are getting a representation of the world as ST. At any given time t, we are getting a representation of the world as ST. Side by side to this representation, we are having in parallel an action encoder running, which is trying to, with the use of the motion prediction network here, they are trying to figure out what kind of flow that you are carrying out. What kind of flow motion, with this SE3 transformation, they're trying to predict out what kind of flow, what kind of motion that you are carrying out. So this is the FT that they are outputting for any particular time t. And this representation, along with the object masks, putting a mask on the object, creates the instance mask empty. And then they are coupled together, and this warping approach is, I think, just like a mapping that they are doing. And finally, they are creating this final warped representation S-T. Oh, I forgot one more thing. Yeah, I forgot one more thing. So what is happening? This ST here is actually generated by a previous S-T-1 that is coming from here. That is coming from the previous time location warped representation, which is the complete output here. It is coming in from here. And using both of the scene and the previous history, it is creating a representation ST at that time. And this one will be creating S-T, which will be used by ST plus 1. ST plus 1 will be using it to create the new one. So the idea is that if we can create, so history is being extracted here. History of the motion is being extracted here. Here, the motion happening at that particular time is being extracted. And here, the object's permanence or object's identity is being assigned. That, hey, this is the object belonging to this particular class that is being moved, or the mask of that particular object is this one. So this is how they are keeping track of different things in their model. Yeah.
So in the low flow, it fuses the previous one and the current state, right?
Yeah, the previous one with the current state model that they are getting. Yeah.
And what about the top one?
It is running in parallel. It is running in parallel. So like they are taking the representation and they are putting it in two different places. Like they are like running one thing for the action part, and so this is the motion prediction, like how the robot is interacting with the world and what kind of motion it is doing. And this is kind of predicting that, hey, for the same grid location, what was the previous thing there? What is the new thing there? So it is kind of aggregating the history over time.
So in the top floor, it only looks at the current scene.
It is looking at the current scene only. It is not taking the previous part. No, this is not going up here. It is only for the motion prediction, like how the motion is happening from that scene to the next scene. Because it is taking the flow information, and so I mean it calculates something like a loss value here, like the mass that it generates from this one. I mean, taking the current scene and the previous scene and the motion that is happening up here, it is going to generate sorry, that is not present. It is going to generate a mask, and this mask with the motion prediction that is happening, they are using MSE error for that to generate they are using the mean square error for that, pixel by pixel, to generate like how good the scene flow is finally coming out to be. So they're using a mean square error loss there to generate that thing. So it is keeping track of the prediction, which is the prediction value is in finally like added to the mask value and the scene representation value to create the next one. So motion, that is the next state that you're going to be, this particular state that you are in, and identity of the objects. So the way I understood is that next state, this particular state having the history of the previous state and which object is what, like identity of the object.
What does TC?
Oh, it is a representation. It is a representation of truncated sign distance function. It was earlier we discussed about like simple kind of like representation of the world. Any more questions, guys, about this part? Because yeah, I mean, this was the tricky part when I was also trying to understand. I don't completely understand it because not run the code, but yeah. And one more thing was there which I am forgetting, which was that I think that this addition that they are doing here, I mean, this SE3 transformation that they are doing, they needed to do it in parallel. They needed to do it in parallel because SE3 transformations, SE3 transformations are there's a reason that they have done that, they've done that separately, because it is a completely different group. I mean, it cannot be added to this particular group. It's like affine motions or like affine mass that they are getting here. So they cannot like add both of them together. They are like in two different representation space. That is why they are like run these two things in parallel. I think so. They are like mentioned that somewhere in the paper. Somewhere in the appendix, I think they have mentioned. So maybe I will be able to get back on that in a more better way. Okay, we can come back to this part like again also. So yeah, I have like written this thing also. So they generate an ST, and ST is the aggregate of the previous data with the depth, and this actually is added to. I mean, it is like aggregated with the previous scene data S-T+1, and an instance mask is generated. So the instance mask creates a model object representation. Like, hey, even if the objects are occluded, still it will create a kind of like a continuous representation or complete representation of that object, even if the object is occluded. And in parallel, a motion predictor tries to find out the motion of the object using the previous data and the scene representation. The previous scene data is the no. This is not correct. The previous scene data is not correct. Just that particular scene representation, because it is not taking in anywhere the information from the previous scene. You're right. It is not taking in the information from anywhere from the previous scene. And the predicted motion and the instance mass are combined to compute. So the predicted motion being this, and the instance mask and the representation is like used to create this one, which is a warped representation. And lastly, the FT is used to warp the scene representation to get the S-T for that time being, for that step, which can be used in the next step. And the benefits of DSR that they are putting in the paper is that since it is using a 3D volumetric representation, so it can create the A model 3D shape regardless of the occlusion, because they are taking a 3D volumetric representation, so it is able to create it. And one more reason we can say it is able to create it is because they are having a history of the object, and the identity of the object is also maintained. So in the beginning, so if your identity of the object is being tracked from the beginning, so the model is able to create the occluded unoccupied grids, which it is occluded unoccupied grids where the object is kind of hidden. So it's able to create that thing. Second is that since the history of the motion is aggregated, so we are able to get the motion flow, and by using the history information, they are able to capture the permanence of the object, and because like they are also keeping a track of the object identity, so they're able to carry out the permanence of the object and the continuity of the object. And this is like what exactly their loss function is like. I'm not kidding. This is their whole loss function: loss in the motion and a factor multiplied with the loss of mask. So the two losses that they are using, the FT loss here, you're using the FT element, and here the loss of the mask element, the MT element. And both of them are MSE losses. So this is what they are using. That factor is, I don't know, dependent upon what. They have just chosen the value to be 5.0 for their paper, but yeah. So this is their model architecture and their loss function. The way they have created the training data, not very clearly written out. I mean, they have not very clearly written. So like they, in the scenes that they create here, they create like they choose 4 objects of like different classes. But in the paper that they have written, 4 different objects out of multiple sizes of cubes, multiple sizes of mugs, bottles, can, phone, and sofa can be chosen at random. So like multiple, I'm not very clear that they are like choosing one instance of each object, or they're choosing multiple instances of the same object, because in the scene that they have put in the paper, the images that they have put in the paper, they're not choosing multiple different objects, or multiple different instances in the same class. And then the location of the objects are created by dropping them at randomly, and pushing happens by taking a manipulator, and they are using a heuristic policy. They have explained that in the appendix a little bit, that hey, this is the world, this is the scene that can be seen by the camera. So you're not supposed to exceed the scene. You're not supposed to move beyond a particular value, and the motion happens at a constant velocity. Like they're trying to create that kind of like motion at the end effect that happens at a constant velocity. So they are keeping these certain heuristics, which they have explained in the appendix. So they have generated 80,000 interactions from the training data. And for the real world that they are doing, they're using a UR5 robot, and it is having a cylindrical pushing tool mounted on the robot. And they are using that to push the object, and they are having track the world around it. They are having 2 RGBD cameras placed here. Like I think the images show it is like real sense camera only. And they are generating 900 interaction steps there. Moving on. So they are performing, I think they are performing 3 different tests. I have put the information about 2 tests only. The third one, I do not think that was that important, so I have not put it here. But they are, so, and the third thing is that, and one more thing is that they are like comparing it against multiple different baseline models, because even though there are like few baseline models which are like doing a 3D representation of the world, there are still a few of them which are like present there. So SE3 is one, SE3 pose is one that they are like comparing it against. So the first test that they are doing is, how accurately are we predicting the object motion under different robot interactions? And the error again is MSE. So MSE error is used, for example, like, hey, the motion happened to like, after the motion, the object is now finally here at this particular like location, and per pixel comparison from the new location compared to the one location that the model has predicted. So that is how they are creating the loss value for this one. There were a few things written that they have done. For example, with the SE3 pose, what is happening is that, so first of all, it is having certain occlusion behind it. And we are seeing that the way the motion happens, object motion and different, if I remember correctly, what they have put up here is that, see, if one object is being moved, when a particular interaction is being carried out, if one object is being moved, so what happens is that just like a few pixels in the scenes are moving, that is what is happening. I'm sorry, they have compared that with SE3 pose and DSR net in some way. I'm forgetting the text material, how they have done that. So I'm trying to come up with something on the go here. it is not something like I'm randomly creating, but like what they have like written in the paper, that they are pushing it with a tool object, and the object is moving. And since it is like a very small number of pixels or total number of pixels, so what happens is that the difference remains very small. So they have to use a metric of per pixel, I think, to enable to like correctly figure it out. And the second thing is that in this one, the map updation does not happen or something like that, like occlusion. So if something remains occluded, that remains always occluded. So this was like one issue with this particular SE3 pose one. But yeah, they were able to. I'm not put, I think, the tables here. No, I not put the tables in the presentation. But yeah, I mean, we can go back and we can like look at the tables in the paper. They have performed the loss comparison with the 3 other baseline models compared to DSRNet, and the DSRNet is performing quite significantly better. The second thing that they have like looked into is that so can the history be aggregated and correctly predicted? That is the permanence of the object and the continuity of the object. Can these things be correctly predicted? So what they have like done here is like different objects being moved. So different instances, different instances of the same object being moved, and can their permanences and can their continuity be preserved over time? So here is our DSR net. This one is being moved, and even though it is being occluded, with the blue one or the green one, because the camera view is from this side. So even though it is being occluded, it is able to correctly predict the instance of the object. However, it is not always certain or sure. We can say, see, for example, here the mask got collapsed. Like this object disappears from the scene, and the mask of this particular object is applied on this one. So it is not predicting that this is the right instance of this particular object. Like when they two got collided, or when they two got occluded, and the camera is like looking from the left-hand side. So here this particular method is having an issue. Here the object completely disappears, and in this one they are having different objects here, different classes here of the same instance, and we can see that again the object disappears here. Again the object disappears here, the object disappears, and object disappears again here. In this one, the object does not completely disappear, but I think the instance changes or something like that. Like for the when the instance changes in some way. Okay, it is disappearing here, but perhaps the instance, the identity of the object changes. So they are using, I forgot that they are using some kind of intersection over union approach. They're like using an unordered versus ordered intersection over union approach. So unordered and ordered is that they are generating this thing. Unordered is that, hey, what is the maximum average value of the IOU masks, IOU masks that are generated, considering all the instance of all the objects, and ordered one was something like different from it. But yeah, that is what they are trying to do here, that trying to maximize the average value of the IOU mask that they can get. So DSR net in the unordered and the ordered one both performs quite well. I mean, this is their paper, so yeah, it performs quite well. Lastly, guys, the third test I have not mentioned here. So lastly, what the takeaways can be for us? Lastly, the few takeaways for us from the paper can be that object continuity is quite well maintained. Like the object's tracking abilities are quite well maintained. The occupancy grids over the time. Motion prediction helps in the history aggregation. So actually, these questions they are asking in terms of this one. Like, not exactly they are performing ablation study in the paper, but hey, the elements that we have added and the approach that we have taken, are those things leading to history aggregation? Are those things object continuity? So object continuity is because of history aggregation, and history aggregation is helped by motion prediction. So this is like motion prediction is helping in figuring out the object continuity. So this is actually happening, that ability to predict the motion correctly because of aggregating the history over time, the S-T, the S-T -1, S-T, S-T +1, so on, is helping in maintaining the object continuity, that is the ID of the object, and how the ID of the object and the grid values in which that object is correctly occupying the space. So that is the A model prediction. So object continuity is being able to maintain that is the ID of the object and how the object is moved, and object permanence does happen. However, it is not completely satisfied for all the instances of the object. This thing that they have mentioned, that object permanence does happen, but like all the objects, so all the instances of particular objects, their permanence are not completely guaranteed as they're finished in the paper. There is an appendix section there that they have where they have explained the heuristics of the motion that they are doing. They are also mentioning what kind of objects that they are choosing and some mode tests that they have performed there. However, I've not got the time to go through it, guys, so I'm sorry about that. But yeah, this is the whole of presentation. Thank you for listening, guys. So yeah, any questions about any particular slide? So yeah. It's kind of like a learning and visual based method that they are combining. So hardly any work on the control side here, but mostly learning and visual based method that they are combining. And
can we combine this with a visual based? Maybe.
I think so, because if we can get the instance mask, yeah, and if the world is kind of confined, the world is very well defined, so the instance mask per pixel can give us the location or the coordinate of the object, and that can be this can be extracted very well because they are doing the loss calculation there, like the MSE loss, or they are doing those things. So if we can get the coordinates or the location very well, we can use that data to figure out that, hey, the object's motion prediction is saying that it will be at that location at that time, and maybe correct it, or this may be the error in the trajectory that is tracking. So yeah, I think it can be used in that way because it is getting that data. So I think so. Yeah, using the instance mask we can do that, and scene flow can be a good predictor about the next step also. I mean, it's imagine if this is the PID part, so this is the D part, there's the P part, and this one would be the whole I part, like the integration of the previous parts of motion. This is the present state, and this is the next state that will be happening. So
If there's no more question, we can end here.
sorry, I think it's small. Yeah.
Okay, thank you.
You're welcome. Thank you. There's more work from a lab, guys. There's more work from a lab, and along the same line. So yeah.